Hey everyone, today we're going to be talking about uniform circular motion and how an object in motion behaves when it's following a uniform path along a circle. And this has to do with when we have some kind of force. Say we have an object, we have some kind of force acting in one direction that's perpendicular to the velocity of the object. It's going to cause this object to move in a circular path. And it's because we have an unbalanced force, which we'll talk about more when we get into Newton's laws shortly after a circular motion here. And that'll become a little bit more clear. But for now, the unbalanced force acts perpendicular to a velocity. It causes the object to move in a uniform circular pattern. As long as it's perpendicular to the velocity, the object moves in a circular path at constant speed and experiences what we call uniform circular motion. And it's uniform because it's not changing. It's constant. In the scope of this class, we're not going to experience anything other than uniform circular motion. Now, if it is moving uniformly, it's going to have what we call centripetal acceleration. And remember, acceleration is a vector quantity. So the centripetal acceleration is acceleration of that object. It's directed toward the center of the circle in which or the path that the object is following, that circular path. And that's represented by the equation a sub c equals v squared over r. And that's going to give us an equation to solve for centripetal acceleration, where r is the radius in meters, v is the speed in meters per second, and the AC is centripetal acceleration, which has the same units as any other acceleration, which are meters per second squared. Now, centripetal acceleration is known as center seeking, meaning that acceleration is seeking the center of the curvature of the path. And that quantity, if we look at our equation here, is directly proportional to the square of the velocity, or the square of the speed. But if we compare the centripetal acceleration to the radius of the path, that is going to be inversely proportional. We want to be aware of those relationships as we look at and work with our centripetal acceleration equation. Now, centripetal acceleration works closely with centripetal force. And we don't want to confuse centripetal with I don't want to say this. Centrifugal force, which if we think about this, and we'll get into this a little bit more later, centripetal force acts towards the center, whereas our centrifugal force acts outwards from the center of the path of the circle. And this has to do with one of Newton's laws, which we'll get into, and it has to do with frames of reference. They're essentially the same force, but it depends on our frame of reference and how we're looking at the situation and which object we're referring to and thinking about when we're dealing with the motion. So the force that's needed to keep this object moving in the circular path is the centripetal force, and it's directed towards the center of the circle. Now our acceleration will act in the same direction as the force when applied, and we'll call that F sub c. And our equation for this is mv squared over r. Now that I'm writing that, I just realized here, when we look at centripetal acceleration, we look at the equation there, v squared over r. the acceleration of that object is independent of its mass. So the acceleration is going to be the same regardless if it's a ball being swung around in the circle or if it's a car driving around a roundabout. The acceleration is independent of the mass. When we look at centripetal force, the force is not independent of the mass. We do have a mass unit there that will affect the kind of force that the object is going to experience, depending on the change in mass. So the units for this are really nothing new. M's our mass in kilograms. V is our speed in meters per second. R is our radius of the circle that we're traveling on, and that's going to be in meters, just like a distance would be. And our centripetal force. This is centripetal force. That's represented in a kilogram times a meter per second squared, which we also call a Newton. So you'll see both of those depending on the application of the problem. So centripetal force, as any force is a vector quantity, and it's directed toward the center of the curvature that produces the acceleration. So we can show this as our F sub c directed towards the center of the circle. And that's what we have right here. Center of circle. On this little dot here, this is going to be some type of body that has some kind of mass. Now if we take a look on this other side here, we always have a velocity vector that's tangential to the path of curvature, and our centripetal acceleration which is v squared over r, is directed towards the center of our circle. Now an object that's in uniform circular motion, traveling at constant speed in its circular path, it continues like this because there really is no net force that's changing its motion. Nothing that's going to cause it to veer off of its path. It certainly can, but when we're talking about uniform motion, there is no net force acting on the object in the direction of its motion. So it's going to remain the same speed. Our velocity magnitude will remain the same. But when we look at the tangential velocity, it's going to be constant. It's going to remain the same as we're traveling in uniform circular motion. However, the object that's traveling in uniform circular motion is certainly not in equilibrium, because we have a centripetal force acting perpendicular to the velocity, and that's going to produce a constant acceleration towards the center of curvature. Meaning our speed remains constant, but the velocity is actually always changing, because if we think about this here, this would be our centripetal force, our velocity, magnitude. So if we look at the length of this line and the length of this line, they're going to stay the same. But what changes is the direction. And since velocity is a vector quantity and has both magnitude and direction, if the direction changes, the velocity changes. This would be our radius here. This little portion here is considered the displacement due to our velocity of v. And this little portion here is our displacement due to the centripetal acceleration. So as the object moves around the circle, its velocity is constantly changing, its acceleration is constantly changing as well, because the direction of the acceleration continues to change as the object moves around the circle. So let's take a look at this in an example. A 3.4 kilogram cart moves in a circular path of 4.1 meters, 4.1 meter radius at a constant speed of 5 meters per second. Determine the magnitude of the centripetal acceleration of the cart, and then we'll determine the magnitude of the centripetal force of the cart. So let's first see what we know. What are our known quantities? Well, we definitely know the mass of the cart. It's 3.4 kilograms. We know the radius of the path, which is 4.1 meters. And we know the velocity of the cart, 5 meters per second. Well, let's see what we don't know. We don't know centripetal acceleration. We don't know the centripetal force. So we're going to solve for each of those. And we'll start with the centripetal acceleration of the cart. And we know that centripetal acceleration is equal to the velocity squared of the object divided by the radius of its curved path. Our velocity is 5 meters per second. We're going to square that, make sure the squared goes on the outside. And we'll divide that by the radius of curvature of the path, which is 4.1 meters. This comes out to 25 meters squared per second squared over 4.1, over 4.1 meters, which gives us 6.2 meters per second squared, as one of our meters will cancel there. So this object, if we think of this cart traveling on a path here, it is experiencing a centripetal acceleration of 6.2 meters per second squared. As this cart moves around the circle. And we know that the radius here is equal to 4.1 meters. Our velocity is 5 meters per second. So to find the centripetal force, or F sub c, we know that we need the mass times the velocity squared divided by the radius. We know the mass of the cart is 3.4 kilograms. Remember, force is affected by the mass of the object times the velocity squared divided by our radius. This will give us 85 kilograms times meter squared per second squared over 4.1 meters. I'm going to bring this down here. This gives us 21 kilograms times a meter per second squared, as our 1 meter canceled there. And this would be equal to, because we have our unit here for force, we'd also call this 21 newtons. That's all I got for you today. Please bring any questions that you have into class. Have a good one.